Today we're going to be talking about organometallic reactions. Organometallic reactions occur when you have an organic molecule that is bound to a halide, and you can react that with a metal. In this case it's just being shown as M, and that metal will insert into the carbon-halogen bond. So the first one that we're going to talk about is one of the classic examples called a Grignard reaction, or a Grignard reagent. So if you take an organic organobromide, chloride, or iodide, it's often done with a bromide, you can react that compound with elemental magnesium. And what's going to happen is the magnesium is going to insert in between the carbon-bromine bond to give you now this Grignard reagent. So Grignard reagents can be thought of with their reactivity as carbon now has a delta negative, or a negative charge, where that magnesium has a positive charge. So that's the opposite of the starting material, where carbon had the delta positive, bromine had the delta negative. So these can often be thought of as carbon with a lone pair of electrons. So mechanistically, we often will draw this kind of species. Now, if you treat a Grignard reagent with water, or in this case, deuterated water, what's going to happen is it's simply going to do an acid-base reaction, and you're going to get a carbon-deuterium bond formed. So again, this acts as a base and deprotonates or dedeuterites the D2O. If you react this with an electrophile, this ends up being a very strong nucleophile. So an electrophile, such as a carbonyl, we can think about how the electrophile acts because there's a delta positive on the carbon and a delta negative on the oxygen. So the carbon is the electrophilic center. The Grignard reagent will add into that electrophilic center. So again, we can show it with the resonance structure or directly onto the carbonyl with this extra set of arrows. So the product ends up being a new carbon-carbon bond formed in red here, and see this ethyl group has been added to the carbonyl. We'll talk about that more next semester. Another thing you can do with Grignard reagents is, or another kind of variation rather, instead of the Grignard reagents, it's called the Gilman reagent. So in the case of the Gilman reagent, what you do is you add lithium instead of magnesium, and you form a carbon-lithium bond. Now in this case, the lithium doesn't stay bound to the halide, so you need two equivalents of lithium, and you end up getting lithium bromide as a side product, as a salt. This is not the Gilman reagent yet. Now you add this reagent to copper iodide, and you get this cuprate species. So you notice that you've added two of these alkyl groups, in this case the methyl group, to the copper group. When you add a Gilman reagent to another alkyl halide, you form a new carbon-carbon bond. So this is a very powerful carbon-carbon bond forming reaction. The key thing to keep in mind is that you have effectively wasted one equivalent of the methyl. So if it's the case of like methyl bromide, that's a very inexpensive alkyl halide. Sometimes this can be a very costly reaction. This will work with alkyl halides such as chloride, bromide, and iodide, but it will not work with alkyl fluoride. That bond is simply too strong. The last type of reaction we're going to talk about are palladium couplings. So in this case, you have an alkyl halide, often a bromide or iodide, or chloride also works, with an aryl halide with an aryl boronic acid. It could also be a boronic ester, but a boronic acid is common. You treat this with palladium, so palladium is the metal. The triphenylphosphine is a ligand on the metal, and you can learn about that in future courses. You treat that in the presence of a base and a solvent, and the key thing here is that you've formed a new carbon-carbon bond between aryl rings. That's something we haven't been able to do before. This particular reaction is called the Suzuki-Miura reaction, or cross-coupling. Suzuki got the Nobel Prize for this. One of the fun facts for you Arizona students is that if this boron instead is a tin atom, this is called a Stille reaction, after Dr. Stille, who was a U of A alum. Unfortunately, he did not receive the Nobel Prize because he had passed away before the time that the Nobel Prize was offered. So the mechanism involved in this reaction involves palladium insertion into the carbon halide bond first, and then into the carbon boron, or carbon tin, if you're talking about Stille reaction bonds, and then the two carbon-carbon bonds form. We're not going to go more into detail about the mechanism of this reaction, but the book talks about it, and this is something you'll learn a lot about in inorganic chemistry in next year. Well, thank you for your time. And actually, one other thing I want to say about this before thanking you for your time is that the interesting thing is you can actually flip. So this halide can also be the boron, or the boron can be the halide. So you can flip the two species, and so you can still form this carbon-carbon bond, but you can change which species had the halide and which species had the boron. I want to thank you for your time, and I look forward to answering your questions in class.